Afternoon, can you hear me? Okay, we have reached the sunset of the conference. It has been, yes, does it work? Esto no trabaja, esto no funciona. Vale, okay. Okay, sorry. There have been many talks, far too many, so I will not be able to cover everything. So I will just try to grasp a few subjects. First of all, let me just summarize with the first slide. I think that it's very clear that we have been extremely successful. It's a great success of the standard model. Finally, we have what we were looking for many years, and it seems to work. In fact, the problem is that it works too well, and we would like to see something which is not a standard. Let me stress that in order to reach this level, it has been necessary a huge amount of work by many people. The colliders are hadronic machines, so we are looking for electroweak phenomena, but the only way to dig into the electroweak phenomena is keeping control of the huge QCD background. In fact, LHC and the Tevatron are QCD machines. And there is a complete army of people working very, very heavily in this issue. You can see here how things have evolved with time. Just 10 years ago, doing a 3-loop calculation was just a dream. But now the standard is next to leading order, and even next to leading order is becoming the state of the art in many processes. So I will not give details. You can just go to the nice review presented by Nasson, where you will have all kinds of references to the original work. But it's amazing that all the processes, or many of the processes that we need, and we are going to need for the next run of the RIT, are already at a level of precision that is quite amazing, quite relevant. Of course, you have seen this plot many times. It keeps updating, and it just shows that the experiment and theory agree over many orders of magnitude. This is a highly non-trivial achievement. It shows that the detectors are working properly, the analysis of the detectors is working properly, but in addition, that the theoretical calculations are at the level of precision that they were supposed to be. We have seen in this conference new data on alpha S at very high energies at the colliders. The colliders are not going to improve our knowledge of alpha S, because at high energies, alpha S is very small, so we are less sensitive to alpha S. However, they are showing us that the running of alpha S predicted over QCD extend up to TeV energies, which is quite amazing that we can control that. Here you have the usual plot of the PDG showing the most precise determinations of alpha S. You can see that lattice dominates. It's nice that now there are several groups that are doing lattice calculations with different assumptions, with different techniques. Uncertainties now are twice as large as they were at the beginning. So the first group who did the calculations is the most precise one. But in any case, with more conservative assumptions, with more systematics that has been checked, it's nice that things agree so that we really know alpha S, we really know perturbative QCD. Aida Alcadra presented a very nice review of the status of lattice calculations. I will not cover all this part, just let me show, for instance, the determinations of the quark masses, which are also getting very precise. Of course, QCD, there are things that we control, and there are things that we don't control so much. The problem is that at low energies, QCD becomes a very non-perturbative theory. The coupling is very strong, so it's still a challenge to solve QCD in this regime. It's a very interesting challenge. And at the same time, experiment is challenging us because in recent years, there have been a complete family of exotic states popping up. So it's a challenge for theorists try to understand the structure of these states. It's not easy, And in particular, it's not easy because none of these states is going to be one of these possibilities. Everything that can mix. So the states will correspond to quantum superpositions of any possibility which has the same quantum numbers. Okay, but this is a real challenge for theory, so progress is slow, but we are more or less reaching that. Another nice feature of QCD is a completely different regime, heavy ion collisions. It's very difficult to understand that from first fundamental principles because we are at a much more macroscopic level, but a picture is emerging of what is happening there, and it seems that relativistic hydrodynamics plays a very fundamental role in some stages of the evolution of the state. Also, in recent times, we have seen evidence for collective phenomena in proton-lead collisions, which has been also quite of a surprise, and it appears to be very interesting. At the more formal level, we had a nice talk by Pepe Barbon this morning. Let me emphasize that things that appear to be very far from reality, like conformal field theory, ADS, and things like that, are in this moment emerging as possible tools to predict phenomena, for instance, in heavy ion physics, which is interesting. But also there start to appear new tools to solve quantum field theory, to solve QCD. It happens in QCD that you are trying to compute a process for LHC. For instance, you need to compute a cross-section which has far too many legs, because that's what experimentalists need to measure. And then you start drawing Feynman diagrams, and there are far too many. You need huge computers to compute all Feynman diagrams, put all the results together, etc. And when you finish the calculation is a very simple formula, a very simple number that just takes one line. So that's telling us that maybe the diagram expansion, in terms of Feynman diagrams, is not necessarily the best tool to perform the calculation, but is the tool that we know, is the tool that we are used to. So in recent years, there have been several techniques developed from formal theory that start to open the way into a new way of computing things. So I expect that there will be progress in the next years. Let's change and let's start looking for physical systems. And let's start by the top. The top is very peculiar. If you just analyze the Yukawa coupling of the top to the Higgs, and you just make a very simple number, you discover that it's 1 to a very good precision. And that's amazing. A coupling that is 1 a priori means non-perturbative physics. Of course, when you do the numbers more carefully and you put the factors of pi and these kind of things, you see that we can do perturbation theory, no problem with that, but loops where the top appears imply very strong corrections. They are the ones that dominate any electroweak observable where they can appear. So we need to take care of that. And of course, you can start making all kind of questions, what that means. The top appears to be very, very different from the other quarks. Those are the Yukawas of the bottom and the charm, for instance. Clearly, it's a sensitive proof of electroweak symmetry breaking. So if you think that maybe electroweak symmetry breaking has something to do with some other strong dynamics that is hidden behind, the top should have many answers about that. So it's very important that we study the top as precisely as possible. And at present, if you ask the question, how much we know about the top, the answer is that not much. We only know that it's a quark that gets produced and it decays into bottom and W. And that's it. Okay? So there is a lot of work to do, and we should find the best way to do this work. So things that have been popping around in recent years, for instance, the forward-backward asymmetry in top production at Fermilab was higher than expected in theoretical calculations. The theoretical calculations have been looked into a lot of detail by several groups, and the results are extremely stable. Everybody agrees that's the result. Experiment at Fermilab has shifted a little bit. This zero measure a lower asymmetry now. So the present situation is that there is still some excess around 2 sigma in the CDF data, but things look pretty consistent with the standard model. At the LHC, you have proton-proton collisions instead of proton-antiproton, so you cannot measure this forward-backward asymmetry, but you can measure a related charge asymmetry, this one. This has been done both by ARLES and CMS, and the results agree with the standard model. So there is nothing spectacular there. Let me make a comment about the top mass. This comment has appeared several times in this conference, but I am not sure that everybody is really aware of that. I mean, we are getting extremely precise in the measurement of the top mass. And as the experiment gets precise, theories start to worry. So there were many theories worried 10 years ago, 15 years ago, a few of them. Now I think the majority of the theories are worried. What's the problem? The problem is that, the problem is that we are reaching an uncertainty below the GB in a quantity which is just a kinematical reconstruction of what you measure. It's kinematics. It's not related to any QCD calculation. And that means that the thing you measure is not properly defined within QCD. And when we need the value of the top mass to do, for instance, electroweak precision test, we need to specify which top mass we are putting into the test. We need to say if it is the MS bar mass, if it is the pole mass, or if something different. Just to get an idea, the difference between the MS bar mass at the top mass scale and the pole mass is about 9 GeV. Okay, so it's not a minor problem. Of course, people is doing the best you can. It's clear that the closest thing related to the observable we measure is the pole mass. Okay, that's why everybody assumes that it is the pole mass. It's a hidden assumption there. But there should be some correction that we have failed to compute. The only real analysis that I am aware, trying to get a proper definition from the JET data, was done by Huang and Stewart a few years ago. They didn't succeed. So they published a couple of 2-3 papers trying. It was very hard. They were able to identify clear shifts of the order of half a GeV with some uncertainty. So the work is not finished. We need to make progress there. Okay, but clearly it's difficult. There are observables where things are easier for the theorist. You compute a cross-section, we know how to compute, we know how to specify the mass, so that's what you should do. Measure the TT bar cross-section, and nowadays, fortunately, is already known to next to leading order, plus next to next leading log resummation. And of course, there are several measurements already. I am showing the most recent one by ARLES. So you get nice measurements of the top mass, but look to the uncertainties. This is the uncertainty of the top mass average above. Okay? The real uncertainty that you have when you try to compute the mass from the cross-section is of the order of 2-3 GeV. So it's much worse. So we need something better than that. Of course, there have been suggestions how to improve these determinations in the colliders. It's not easy, but it seems that it will be possible, or it should be possible, to reach 1 GeV precision. The problem is that 1 GeV precision is not enough for what we want in an electroweak precision test, and what we want in many other things. Having a jump of 1 order of magnitude in precision will require an E plus E minus machine working in the TT bar threshold, so that's something one should keep in mind. It's an important measurement. Okay, let's go to the Higgs. That's what has been fun in the last couple of years. Now we know that we have this object there. We know the mass. Experiments start to be precise. We start to know many things. So this is really a beautiful discovery. It's a beautiful discovery independently of whatever this object is. Because what we know that it's a boson, that's clear, And now I think it's pretty clear that we know that it's also J equals 0, a scalar. Okay? Experiments have been looking into many other possibilities, and they have been excluding at some confidence level, which is above 90%. Okay? So it appears that it's really a scalar. So now the question is it a fundamental boson or is something composite? If it is a fundamental boson, we have discovered a new interaction, which is not gauge. Of course, it appears to be the interaction of the standard model. Okay? But even if it is not the standard model, it's a new interaction. And it's an interaction of a different nature. That's what is important of this discovery. Up to now, all the fundamental interactions were gauge interactions. You can argue that maybe it's not a fundamental boson, it's a composite boson at some very high scale. But if it is a composite boson, there should be a new interaction responsible for this composite boson. So there is new underlying dynamics. So whatever it is something new, it is something fundamental, it is something that really merits a Nobel Prize. Now you can start asking questions. Theories don't like scalars. Why theories don't like scalars? Because scalars usually have problems when you introduce the scalars into a quantum field theory. The problem is that you put your scalar, it has some mass. Imagine that there is some new physics scale. And it's important that this assumption, if there is no new physics scale, whatever I am going to say now, forget about it. Okay? But if there is a new physics scale, this new physics scale will appear through quantum corrections. And if there is nothing protecting our scalar field, quantum corrections to the mass will be proportional to the mass square of this new physics scale. And therefore, unless you protect your scalar field, the mass will go up. So the question is, which symmetry keeps the Higgs mass from the new physics scale, whatever it is? Because we believe that there should be a new physics scale. Fermions are protected by chiral symmetries. That's why theories like fermions. Gauge bosons are protected by gauge symmetry. We don't know the symmetry which protects the scalar boson. Supersymmetry is or was a possibility. Maybe some scale conformal symmetry. That's something that we need really to work out. What are the possible scenarios of electroweak symmetry breaking? Well, the most probable one, the data is telling us that it's just the standard model. Everything seems to agree with that. But there are alternative possibilities. There could be additional scalar doublets and singlets. This will satisfy still the electroweak precision test, the ratio between the W mass and the Z mass. That will be fine. Of course, the question is if there is one scalar, why there should not be many? So that's something that we should investigate. A third possibility is the dynamical electroweak symmetry breaking, some strong dynamics behind. So our Higgs will be some composite state, either a scalar resonance or, more probable, because it has a very light mass, some kind of pseudo-Goldstone boson of some unknown symmetry. You have already seen this nice list of questions presented by Christophe Grosjean. You can go through it. Everything that is listed there is relevant, okay? And we don't really know the answer to all these questions. Okay, so I will go to some of them, not all of them, but these questions remain to be investigated. They remain to be answered. Okay, I said that the standard model is the simplest possibility, is the one that data appears to be telling us. In fact, you have seen these plots many times, and you see that the values of the Higgs and the top that you extract from electroweak precision test agree with the values of the Higgs on the top that you measure experimentally. If you look more into detail, you could see that really the electroweak precision test will like a slightly heavier top. Okay? But here my comment about the pole mass is relevant because all these tests assume that we know the pole top mass with an uncertainty of 0.6 GeV. And this is not true. Which means that when we plot here 68% confidence level, 95% confidence level, I am not really sure if these confidence levels should be interpreted that way. So we need to be careful. If you look into here, you see that maybe the data will prefer a slightly lighter Higgs mass, but both kind of things are correlated. In any case, the agreement is extremely good, surprisingly good, I will say. Let's analyze the scalar potential. In the standard model, the scalar potential has two parameters. We knew already one of them from mu and decay. Now we have measured the Higgs mass, so we know the second parameter. So we know lambda. And lambda is 0.13, a pretty small number, a pretty perturbative number, nothing spectacular. Here, by the way, you see the loop correction to the Higgs mass. So Higgs mass squared is equal to twice lambda v squared. That's the three-level relation. And now comes the loop correction. The loop correction is dominated by the top, because the top is very heavy. U kava times V, that's the top mass. So that's the correction proportional to the top mass squared. So here you see the famous hierarchy problem, which is not a problem in this framework. Which is the heaviest mass scale in the standard model? The top. So in the moment you compute quantum corrections, you get a correction proportional to the top mass squared, so the Higgs has a tendency to approach the top. And not surprisingly, the top and the Higgs are more or less in the same mass regime. So we understand what is going on. But of course, it's the standard model. And in the standard model, by definition, there is no new physics scale. Those are the scales of the model. But you can turn the relation around and say, okay, we have measured the top mass, we have measured the Higgs mass, so let's extract lambda at the quantum level, the quartic parameter in the scalar potential. Lambda, once you put quantum correction, depends on your renormalization scale, because here you have a dependence on the renormalization scale, and they compensate each other. So you get this plot, where now this is the renormalization scale. And as you go to higher and higher values of the renormalization scale, if you want energies, lambda gets smaller and smaller and smaller. So the standard model works extremely well all the way up to 10 to the 10 GeV, a very high energy scale. And once you reach around 10 to the 10 GeV, lambda crosses 0, becomes negative, which means that your potential does not work properly anymore. It becomes unstable. But of course, you are assuming only standard model interactions. You are assuming that there is no new physics until 10 to the 10 GeV, which nobody believes. Okay? But this just shows you that the standard model as a renormalizable theory is working extremely well. You can turn things around where it crosses exactly. Now is where the comment about the top mass is relevant. It depends on the value of the top mass you put in. Okay? You can turn things around and you say, okay, what happens if that becomes negative and there is no new physics at any scale? Well, your potential is not well behaved. Things become unstable, and then you start talking about the instability or meta-instability of the universe. Okay? And if you make the very strong assumption that there is no new physics at any scale, then you get the surprising result that for the values of the top and the Higgs that we measure, our universe is not really stable, but it has such a large lifetime that nobody cares. It's metastable. In fact, in order not to cross this line, the 0, below the top mass, we will need a Higgs mass heavier than 129 GeV, or a top mass lighter than 171 GeV. So we are very close to criticality, which is amazing. And of course, you could start thinking, the real thing for me is here. Okay? It appears that at some high energy point, lambda goes to 0. Maybe instead of going up, we should start thinking maybe there is some new physics scale with some particular symmetry which forces lambda at this new scale to be 0. It could be some conformal symmetry, for instance. Lambda equal to 0 means that there are no scales. Okay? And then we go the opposite direction and we reach the values we know. In any case, as emphasized several times by Branchina and this conference and many other conferences, you have a strong assumption, is that there is no new physics at any place. In the moment you start playing with new physics, even at the Planck scale, things will change, of course. Okay, you have seen that many times. So we have measured the Higgs couplings, and everything really follows nicely what is expected in the standard model. So you can parameterize things as a power of mass. Remember, fermions coupled to the Higgs proportional to the mass, bosons proportional to the mass square, so you can arrange that to make everything linear, and it is linear. So we have measured the Higgs coupling to W and Z directly, to top indirectly, and now we have already a strong evidence of the coupling to fermions, to tau and B. Okay? So we really need to check all the different couplings. Coupling to the top, at the moment, we only have indirect evidence through Higgs going to photons, because we have this interference. Here we are sensitive. We also, in Higgs production, we have the top. Okay? And that's why we see that everything is consistent with the coupling of the standard model. Of course, this test could be modified by new objects, for instance, running here. A charge scalar will be the simplest possibility. So it's important to get the direct tree-level sensitivity, and it's through the TT bar H production, and it's just a question to accumulate the statistics. Okay, let's go to flavor. You have seen this plot many times. I will not enter into the details of the plot. Probably you don't want that I do that, because there is high technology behind that. A lot of very cute experimental measurements and a lot of QCD calculations. But, so life is difficult, life is tough. People try to reach the best precision they can. But once you do all the measurements, surprise, everything is consistent with a very good precision with the CKM mechanism. 10 years ago, nobody was expecting that. Because the CKM mechanism is just, you diagonalize some matrices, and the gene mechanism appears, okay, but there are many things you don't understand there. Things work, and things work with an unbelievable precision. And it doesn't matter whatever you do. You take all the things which are put there, and you start separating processes that are dominated by tree-level physics, and you get the same answer. You look to processes that are generated just by quantum loops, you get the same answer. You look to only CP conserving processes, you get the same answer, and you prove that CP violation is there. You look only to CP violating processes, and you get the same answer. So everything is really consistent. And it's telling us that the CKM matrix has this peculiar hierarchy, this peculiar structure, that the standard model accommodates, no problem with that, but we don't have any idea where this structure comes from. Let me say that behind all that, there is a lot of work, and Ida was summarizing this also nicely the other day. Well, why flavor physics is important? Because we really need to understand this structure. And we should keep in mind that all this flavor physics comes from the Yucabas. The Yucabas comes from the Higgs. So everything is related with the electroweak symmetry breaking. So we need to do both things at the same time. And both things should be done precisely. And what we need to investigate is what is the source of flavor. If you throw away the Yucabas, the standard model is perfectly flavor symmetric. The three generations are exactly the same. It's only when you put the Yucabas, this huge flavor symmetry gets broken, and we are just measuring the way this symmetry is broken through the Yucabas. But where this breaking comes from, we don't know. You can play with the idea, and now I did a mess, okay? You can play with the idea that there should be some new physics explaining that. This new physics should be related to the Higgs sector, of course. But then you try to put this new physics, for instance, in loops. It doesn't matter whether are quarks or leptons. The comments apply the same thing to the two walls. When you start looking into that, you discover the standard model is very clever. The Jim mechanism is all the time working behind any prediction. And in the moment you do any kind of new physics, you destroy that, which means that you go into disaster. And what you learn immediately is that in the moment you put some new physics that contributes to your flavor observables, this new physics should be either very, very heavy, so that you will never see it. That's one possibility. The other possibility is if it is not so heavy, the couplings cannot be generic in flavor. They should have exactly or very closely the same pattern of flavor symmetry breaking as the standard model. And it's quite easy to understand that. Let me just put as an example meson anti-meson mixing. So we have the standard model, that's the normal contributions. For instance, this is B0 mixing. And now you assume some higher mass physics at some scale. You do that putting all the operators, in this case are operators of dimension 6 that will contribute. They will contribute with some unknown coupling. Since they have dimension 6, they will be suppressed by 2 powers of the new physics mass scale. Now, you study how these operators contribute to B0 mixing is measured. So you immediately get a bound on the coupling divided by the new physics scale square. And since the standard model is working very, very well, you get a tough coupling. Now you can do several games with this coupling. Let's assume that you say, okay, let's put a constant of order 1. Okay? What this exercise tells us about the scale? Well, it tells us that the new scale should be above 100 TeV, or even more. Okay? Completely outside the reach of colliders. The other possibility, which I believe more probable one, is let me assume that there is new physics at 1 TeV, or 2 TeV, or 3 TeV, and this physics is related to flavor. Okay? If you put here 1 TeV, now the bound is a bound on the coupling, so the coupling should be 10 to the minus 5, 10 to the minus 6, 10 to the minus 7. Why? Because in the standard model, it's 10 to the minus 5, 10 to the minus 6, 10 to the minus 7. Because in the standard model, all these flavor contributions are strongly suppressed by the Jim mechanism. So the only way that your new theory can be competitive is inheriting the same kind of Jim suppression that has the standard model. And that's why things like minimal flavor violation have got so popular, because the idea is the following. The standard model without UCAVAs is completely symmetric in flavor. Now, some new physics that we don't know, is breaking the symmetry in flavor space in a given direction. Okay? And now this direction appears in all operators which have to do with flavor. And of course, this direction is the one that we already see in the CKM matrix. Okay? So in the moment you impose that the structure of your UCAVA matrices goes in the same way, the flavor structure goes in the same way to whatever new physics you put, you automatically satisfy the experimental constraints, and you automatically get a lot of space for new physics. Okay, you have seen this slide several times already. I just mentioned it because among the many flavor measurements, those are the things which are new, which means that the previous triangle had to do with the BD system. This has to do with the BS system. And the BS system appears to, again, work in agreement with the standard model, except for this funny discrepancy coming from the D0 data that nobody understands. These are the semileptonic B asymmetries. That's the BD semileptonic asymmetry measured by the B factories. This is the BS semileptonic asymmetry measured by LHCb. This is the standard model prediction, so everything is in agreement. D0 measures something different, is a immune asymmetry, and they are slightly off. But unfortunately, nobody has checked that in a different experiment, so this will remain with us. Okay. We have also seen a nice talk on rare decays. Why rare decays are important? Because in the standard model, they only appear at the one loop level. They are therefore very, very, very suppressed. Therefore, it's easier for new physics to pop out. Of course, it will pop out also at the one loop level. The most recent mode that has been measured is B going to mu plus mu minus. Uncertainties are still very large, both for BS and for BD, and you see that the experiment and theory agree. So therefore, for the moment, we can only get bounds on new physics possibilities, either scalar contributions or even supersymmetry. Okay, let me skip that because it has been already mentioned in several talks. Let's go to lepton flavor violation. Up to now, we were measuring or putting bounds on lepton flavor violation in all possible ways. The most stringent constraints are coming from muon and from tau decays. But now, for the first time, we have already a bound on the lepton flavor violating coupling of the Higgs itself. So the branching ratio Higgs into muon and a tau, we know already that is below 1.6%. So let's just put arbitrary couplings of the Higgs to leptons of different flavor. So in this plot, you have the mu tau coupling, the tau mu coupling, and what this branching ratio means is that we have a bound here along this black line, and what is amazing is that this is a bound which is already better than the one you get from tau decay. Why tau decay? Because if you put these couplings, then the exchange of a Higgs will generate a lepton flavor violating tau decay. And in this way, from tau decay, you can put bounds on these couplings, and you can put bounds there. So things start to get correlated, and I am sure this is the first result. I expect things will evolve in the next few years. Since everything is a standard, let me show something non-standard and at the same time very simple. So what is the simplest change we can do to the standard model scalar sector? Just add a second doublet. That's what supersymmetry does, for instance. Okay, but you can do that without any supersymmetric assumption. In this case, you get 5 scalars, 3 are neutrals, and then you have a charge 1 with the 2 possible charges. The first thing you learn in full generality is that the coupling of the standard model Higgs to the vector bosons gets shared by the 3 neutral scalars, which means that in this kind of a scheme, when you measure the coupling of the Higgs to WW or to ZZ, you should always find something smaller than the standard model coupling. The fact that the experiment tells us that it's very close to the standard model coupling tells us that the mixing about the 3 scalars is very small. In fact, if you assume a CP conserving scalar potential, only 2 scalars that are CP even mix among themselves, and what the Higgs data is telling us is that the cosinus of this angle is basically 1. It's 0.9 at some confidence level. Let's look to the Yucabas. This is where things get interesting. And here you will understand immediately why the CKM structure is so special. So the only thing that you do is you take the standard model Yucaba and you duplicate it. I am just taking the one corresponding to the right-handed W, but you do the same with the right-handed up and with the right-handed charge lepton. So instead of 1 Yucaba matrices, you have 2. Now you do spontaneous symmetry breaking. The Higgs acquires a vacuum expectation value. So you get a combination of the 2 doublets, which gives the fermion masses. And the orthogonal combination gives some Yucaba structure, which is not related to the first structure in any way. Which means that now you do the usual diagonalization of the mass matrix to find the mass eigenstates. And when you diagonalize this matrix, you don't diagonalize the other Yucaba matrix because they are not correlated. so you face disaster, because you get flavor-changing neutral currents, neutral scalars which violate flavor. They couple to up and top, for instance, and therefore you have a big experimental problem. Okay? This happens here, but this happens in any kind of a new physics model where you touch the flavor sector. Okay? So what are the solutions? Well, the solutions for many years, the most simplest one is, okay, if the problem is that there are two structures, you put one of them to 0, and that's it. Okay, that's called natural flavor conservation, and that's what the usual models that you fit in experiment do. You can implement that imposing some discrete symmetry. They are called Z2 symmetries, and there are 4 different ways of doing that, okay, which are called type 1, type 2, type 3, type 4, or some other names. A more general possibility is to say minimal flavor violation. So remember, flavor gets broken in some particular direction in flavor space for some reason that we don't know, okay? So let's assume that the two matrices get broken exactly in the same direction. That means that one is proportional to the other one. That's called alignment. In fact, the first possibility is just a particular case of this possibility. The proportionality constant can be 0 or infinity, and you go to the first case. But this gives a much more general possibility, which in addition allows you to have CP violation, while at the same time protecting you from flavor-changing neutral currents. In the first possibility, flavor-changing neutral currents are absent at all orders because there is a symmetry protecting you. In the second possibility, there are quantum corrections that misalign the flavor structure, but there are flavor symmetries working behind that make sure that this misalignment is so small that you don't see experimentally. So it's something perfectly allowed experimentally. There is a third possibility that has been discussed at this conference, and is imposing some particular symmetries that allow flavor-changing neutral currents to be there, but at a controllable level. This is more sophisticated, so I will not have time to enter into that. Bounds. There is the usual analysis, assuming that only one of the couplings is there and the other one is 0. So type 1, type 2, type 3, type 4. These are the kind of UCAVAs in standard model units, and you see that these are just the values of these alignment parameters, which take some particular values with people parameterized in terms of tangent beta. We know experimentally that the gauge coupling of the Higgs is basically the standard model 1, and that's why when you plot the data, you see that the only region that is allowed is the one where the mixing angle gives cosinus of alpha tilde going to 1. Okay, so it's very, very restrictive, and this will improve with data. But this is with this particular possibility. Remember, you are just putting by hand one of the structures equal to 0. If you allow the more general possibility, things change quite a lot. In the same data, you discover that you have a much more large freedom in parameter space. Just to have an idea, these are the experimental couplings that you get from the LHC and flavor data. This black line, the small line, is the region of parameter space that is allowed in the usual type 2 model. Okay, so you are opening completely the range of possibilities that you can study at the LHC. In addition, in the type 2 model, the charge Higgs should be heavier than 320 GeV, because otherwise BS photon goes wrong. But this is, again, something very, very peculiar of this particular model. In full generality, the charge Higgs mass could be as low as 100 GeV without violating any experimental bound. So it's worth to look into it, because there could be hidden objects that we didn't see so far. Let's go to neutrinos. So all my comments about flavor remain valid here, but of course, what we see from all the beautiful oscillation data is that flavomixing is very different in the lepton sector. Okay? The structure is completely different. We don't understand the structure in the quark sector. We don't understand the structure in the lepton sector. We only know what the structure is. Okay? So we need to investigate that. We also know that neutrinos have masses, and what we know from oscillation data are the mass differences, which are tiny. Manfred Lindner was showing us that from cosmology, we also know the absolute scale of the mass. So neutrinos really have a tiny mass, and we need to understand that. Which kind of open questions are hidden before all the complexity of the neutrino data? Which things we need to understand? Well, you have heard that many times. We still don't know the mass hierarchy, but we know already experimental proposals that should be able to address that. We don't know whether the neutrinos are of the direct type of Majorana type. That's very important. Majorana will mean that lepton number is violated. Okay? And again, there are plenty of experiments trying to analyze that. We don't know there are sterile neutrinos. We don't know whether CP violation is there. The oscillation data seems to hint that CP violation is favored, but we need to figure that more clearly. Of course, the question of baryogenesis, leptogenesis, and so on is an open problem, and flavosymmetries. We are lacking a theory of flavor. Let me do a very simple exercise. You just take the standard model, you adopt an effective field theory language, so you don't assume any right-handed neutrino. You only assume the objects you have measured, the standard model, fermions, and bosons. You build all possible operators with the lowest possible dimension, and of course, which dimension you expect to dominate? The lowest one, dimension 5. If you go to dimension 5, there is only one possible operator. It was worked out by Weinberg many years ago. It has this form. It only affects leptons. And then when you put here the Higgs vacuum expectation value, this operator generates a Majorana mass term for the left-handed neutrinos. And in this Majorana mass term, if you analyze it, you can immediately identify all kinds of seesaws. The seesaws are just particular implementations of this mechanism. So the neutrino mass is suppressed by the scale of new physics, is proportional to V squared, the vacuum expectation value of the Higgs squared, times some coupling. We already know that there is a small mass. Okay, so if you put numbers, the scale of this mass, then what you discover is that the scale of new physics, of course, divided by the coupling, you cannot separate both things, is of the order of the grand unification scale, which is amazing. Okay, let's go to supersymmetry. Fortunately, the Quixote and Sancho Panza exemplify quite well the feelings of half and half the community about the present status of supersymmetry. What's the problem? Sorry. The problem is this chart. Okay, it's amazing how experiment has progressed. Of course, in this chart, there are plenty of different measurements, plenty of different assumptions, plenty of possible holes here and there where you can still wiggle a little bit. But clearly, the scale is going up. And that's not what we wanted it to have. So in one side, we have very strong experimental limits on the SUSY partners. On the other side, we have a measurement of the Higgs mass. It's light, but it's not so light as SUSY would like it to be. At tree level, the supersymmetric prediction is that the Higgs mass should be below the Z mass. Of course, we discovered already in the times of LEP that because the top is heavy, there is a very large correction proportional to the top mass. Okay, and this large correction makes the Higgs mass go up, but there is tension with the present value of the measurement. Tension means that the usual constrained supersymmetric models face difficulties. There are improved higher order calculations that alleviate a little bit this tension when you include the resummation of large logs and things like that. But the tension is there, and the tension is pointing out that the scale of supersymmetry should be large. If you just rely in the constraint schemes, constraint means that you take the huge supersymmetric parameter space of the order of 120 parameters, and you reduce it to just 4 or 5 parameters, then you have difficulties. Of course, in the moment you allow more freedom, what is called a phenomenological minimal supersymmetric standard model, so you allow 19, 10, 20 parameters, and you do a small Monte Carlo, and try to see, you generate models and models and models, and try to see how many models agree with data, you get this type of plot, which tells you that many possibilities are excluded, that many others are still allowed, so we should not give up. The problem is that this now is a data-driven search, because there are far too many parameters. There are many, many SUSY variants trying to accommodate the data, so you have all kinds of possibilities. Of course, the problem is naturalness, as Marcela Carena was nicely explaining the other day. Since the supersymmetric scale goes up, then it's not clear that supersymmetry is protecting the scalar boson from high corrections. But it's not only a supersymmetric problem. We have plenty of results from the colliders that are telling us that all kinds of exotic objects are going to higher and higher scales. And here again, we could think about the Quixote and the reaction of Sancho Panza when we are trying to fight and trying to really find all these monsters. Okay, what the situation appears from a theoretical point of view. Data is telling us that probably the scale of new physics is high, so we should do effective field theory. Effective field theory means you take the objects you know, the particles you see in your spectra, you build operators in terms of these particles suppressed by the new physics scale, you don't know where the new physics scale, and now you try to do precision physics. The standard model corresponds to dimension 4. The first correction is dimension 5, only is relevant for neutrino physics, but we already know that the scale is very high, so it's going to be relevant here. So the leading corrections will have dimension 6. For instance, you can think about muon decay, is the same kind of thing. You have a new object which couples to the standard model objects with some coupling. You exchange this object, you will have a dimension 6 operator as a result, proportional to coupling squared divided by the mass of the new object squared. Okay, and this type of correction, the one that we can really constrain from data. But of course, we have many options. There is not a unique field theory, because you need to decide which are the objects that we know. And for instance, you need to decide what the Higgs is. If you decide that it's an SU2 doublet as in the standard model, you get one effective field theory. If you decide, no, let's say that it's a scalar singlet, then you get a different theory. Or you could say, for instance, additional light scalars are not excluded. Okay. In next year or in 2 years' time, we could discover a charged Higgs, one additional neutral scalar. Then you should put those objects into your low energy effective theory and construct the operators with those objects. It will be a different effective field theory. So there is a lot of work there to do, and we need to dig into this work to investigate that. More things. Probably you heard many times about custodial symmetry. What is custodial symmetry? It's something very trivial. You take the scalar potential of the standard model, you just do a couple of field redefinitions, so you take the scalar doublet, the charge conjugate of the scalar doublet, you extract the Higgs, and you leave the exponential of SU2 phases. Those are the Goldstone bosons. Okay? Those Goldstone bosons are the ones that give the mass to the W and to the Z. And they have this Lagrangian, plus things that depend on the Higgs. This Lagrangian is the same Lagrangian that describes the physics of pions in very low energy QCD. Exactly the same Lagrangian. Why? Because the scalar model sector has exactly the same symmetry that low energy QCD has. Okay, that's custodial symmetry, so you can make theories which are even more general, effective field theories, where you do an effective field theory of the Goldstones, the things that we are sure that they are there because we know the masses of the W and the Z. And now in this effective field theory, you need to implement the Higgs as a singlet. What happens when you do that? It happens here or it happens in the more normal scenarios with the Higgs doublet. For instance, you compute W scattering, longitudinal W, except for the Higgs contribution is the same formula that describes pion scattering at low energies. So you just take and modify the gauge couplings to the Higgs. So in the standard model, A and B are 1, so you just put A and B. Now you compute how this cross-section behaves at high energies. At 3 level, it grows like S. At the 1 loop level, it grows like S squared. A disaster. It violates unitarity. This tells you that in the moment you modify the gauge couplings of the Higgs, you are going to have plenty of scattering amplitudes, the ones related with longitudinal Ws and Zs, which grow with energy, and therefore they violate unitarity. In the standard model, A and B are 1, so all that disappear, and of course, the cross-section does not grow. Unitarity is preserved. If you see a modification of the gauge couplings, that's why it's so important to measure very precisely those gauge couplings. Any modification of those couplings will imply that there should be additional states to restore unitarity, either in a perturbative way, for instance, additional scalars, or in a non-perturbative way, if there is some strong dynamics behind that. It's nice, it's the opposite, sorry. It's nice that at this conference, we have seen the first evidence, experimental evidence, of WW scattering at LHC. Uncertainties are still very large, but the game is just starting. Okay, so we just need to accumulate the statistics and learn about these kind of things. And of course, we had many kind of theoretical contributions trying to play with all kind of strongly coupled dynamics associated to that. Well, my time is over. Fortunately, most of what I was going to say about dark matter and things like that has been already covered in the previous talk. Okay, for instance, now it's very popular. Dark matter is one of the things that supersymmetry likes because you have plenty of candidates, but there are many other options, plenty of beyond standard model options that are able to generate dark matter candidates. Okay, so I need to skip all that, but you have seen already it in the previous talk. Let me just make a comment to finish about inflation. We have seen a very nice special session with the data has been presented. Alan Guth gave a superb talk explaining the basis of inflation. What we know? Well, we know Planck is telling us that omega is 1 with a miserable precision. BCEP2, if gets confirmed, it's telling us that the energy density of the inflation is of the order of the grand supersymmetric scale, Wood scale. It's interesting. Of course, we need to wait and see whether this is a real signal, whether there is dust, something like that, so I cannot say anything about that, only that is interesting. And in the last 2-3 months, there have been so many theoretical papers that I have not been able to read even 1/10 of them. Okay, so physics is interesting. Let me just mention one thing. All these papers, hundreds of papers, that were trying to develop better the inflation scenario in order to accommodate the BCEP2 data, all of them are playing with the scalar fields. So we say at the beginning that we didn't like scalars. We have discovered already one, the Higgs. Okay? Maybe there are more. That could be a good signal of that. Okay, so scalars are interesting. Or there is the second possibility, maybe the Higgs could be the inflaton. Is Higgs inflation a possibility? Well, the first answer, the immediate answer to everybody is no, because the parameters of Higgs inflations are already fixed by the Kobe data, and once, so you get the predictions on the usual inflation parameters, and they disagree strongly with ICHEP2. However, immediately after ICHEP2, Berkov and Shaposhnikov reevaluated their previous calculations, and they found something peculiar. What they found is because the standard model scalar coupling has this instability, if you assume that there is nothing else but the standard model and the Higgs, you find that inflation is only possible for Higgs masses above some critical scale, which happens to be close to the Higgs mass. But moreover, if the Higgs mass is real close to this critical scale, they don't trust anymore their calculation, because quantum corrections are quite unstable, and the result depend extremely from the exact values of the Higgs mass and of the top mass. And we don't know the exact value of the top mass. Okay, of course, this is one possibility. There are many others, but it just means that the better we measure parameters as precisely as possible, because sooner or later we are going to need that. So let me conclude, because my time is over. I put already my conclusion in the first slide. The standard model is working beautifully. However, there are many things we don't understand. Among them, I think one of the most obvious ones is flavor, both in the quark and lepton sectors. We don't understand this structure. There should be new physics behind that. But you have many other things, CP, baryogenesis, dark matter, cosmology. So there are plenty of questions. We need answers. The only thing we know is that there should be new physics to answer that. Unfortunately, don't ask too much guidance from theories. Okay? 5 years ago, we could say very strongly, either you find the Higgs or you find something below 1 TeV. But you found it. Okay? So now we don't know how far the scale of new physics is. We only know that we are sure that there is new physics. Okay? But is it 1 TeV? Is it 10 TeV? Is it 100 TeV? I don't know. We don't know which symmetry keeps the Higgs mass away from this new physics scale. Maybe supersymmetry, or maybe something else. Okay? And conformal symmetry appears to be a quite good candidate. We don't know which kind of new physics. The only thing I am sure is whatever the new physics is, it will come with a whole family of new objects that should pop up in the experiment. So let's wait. I'm sure the LHC is going to work very soon at higher energies with improved tools. So I am sure that there will be great discoveries. Thank you very much.
Thank you, Professor Peach, for your very impressive summary of theoretical challenges and corresponding highlights of the conferences. Unfortunately, we don't left with the time for discussions and questions, but maybe there is just one but very important question. Please, we may sound it. If anybody has such a very important question, Mark. If not, thanks speaker once again.
Okay, thank you.